So we've seen the standard normal distribution in the previous sublecture, and now we turn to the chi-square distribution. And the chi-square distribution is often used to model variance, or when we are trying to understand something about our null hypotheses that involves the variance. And like the variance, which is, of course, the square of sums, the chi-square is also a sum of squares. So like the variance, which is the sum of squares, the chi-square is also the sum of squares. And the chi-square is simply the square of a standard normal distribution taken k times. So k, which is sometimes referred to as the degrees of freedom, if k is 5, you simply sample once from the standard normal distribution, square that, and then sum 5 of those samplings in order to get the chi-square distribution. And as always, there is d chi-square, p chi-square, q chi-square, and r chi-square for the probability density function, the cumulative distribution function, the inverse cumulative distribution function, and random sampling, as there has been for every single prefix, or these prefixes have been consistent for all of the distributions that we've looked at in R. So we don't need to review these. You guys already know how to use them. As we've done for many other distributions, we can do a quick sanity check to make sure that we understand what R is telling us when we type d chi-square. So in this case, I set the degrees of freedom to 5. So I'm going to, I simply sample once from the standard normal distribution with a mean of 0 and a standard deviation of 1. And I sum 5 such samplings squared. And I remember that result, and I do that 10,000 times, and I graph out the results as the bins of my histogram. And of course, the bins of the histogram perfectly match, because I have 10,000 trials, which is a relatively large number. They perfectly matched the expected theoretical distribution that's given to us by d chi-square. Notice the chi-square distribution, because it is a sum of squares, it can never be negative, right? There's no way to have a negative number here. So the chi-square distribution is always pinned at 0 on the left hand of your x-axis of your probability density function. And like the normal distribution upon which it's based, it's defined out to infinity. Now, of course, with the degrees of freedom of 5, you're not very likely to have, or you have a very, very small probability of seeing this number be 30 or 35 or 1,000 or a million, but that number is not exactly 0. It approaches 0 in the same way that the normal distribution approaches 0 as you move more and more standard deviations away from the center of whatever your normal distribution is. As the chi-square distribution gets larger, right, it's always pinned at 0. So at small chi-square distributions, you have this big bulge of the probability density function near 0. This is going to be important for correcting our estimates of standard deviation from sample populations at small sample sizes, that we have this sort of bulge near 0. That bulge near 0 tends to flatten out as the chi-square distribution increases. We'll state without proof that the average value, the average expected value of the chi-square distribution is actually k, is the degrees of freedom itself. So the peak of all of these curves is the peak of the sum of the chi-square distribution, the expected value. Excuse me. The expected value of the chi-square distribution is simply the degrees of freedom itself. Here with degrees of freedom 5, I grab a whole bunch of chi-square sums, and the mean of those is very close to 5. And by the law of large numbers, if there was an infinite sample size here, then the average value would become exactly 5. So just like there is a t-test for the t-distribution and a binomial test for the binomial distribution and a Pearson test for the Pearson distribution, there's a chi-square test for the chi-square distribution. And the chi-square test is used can be used whenever you have a table of numbers. And the null hypothesis, so here is an example from the chi-square test documentation, which shows Democrats, independents, and Republicans versus gender. And the null hypothesis for a chi-square test is that the rows and the columns are independent. And it doesn't matter if you transpose this, so it doesn't matter if you put Democrats along the rows and gender along the columns, or you could switch it and have party affiliation among the columns and gender among the rows. The chi-square test is exactly the same whether you transpose it or not. So this transposition does not matter for the chi-square test. And the way the chi-square test works is that the argument is that you have these values, which we'll call O. These are the observed values. And if you compare those to the expected values and appropriately normalize them by dividing by the expected values, this value itself is chi-square distributed. The null hypothesis is captured by the chi-square distribution in this case. And again, this makes some intuitive sense because this is a square, right? So this square here is captured. The null hypothesis, which is meant by this square, is captured by the chi-square distribution. So we already know these observed values. How do we calculate the expected values? So the expected values can be found by considering only the sums of the rows and the columns without actually considering any interaction between the rows and the columns. So to demonstrate this, let's just simplify this contingency table. We'll come back to this 3x2 table in a second, but let's just consider a 2x2 just to make the math a little bit simpler for this demonstration of how to get the expected values. In order to get the expected values, we only consider the column, the column sums and the row sums, right? So there are 140 males, there's 130 females, there's 120 Democrats, there's 150 Republicans in this simplified 2x2 table. So we can just consider the probability of being a Democrat as 120 over 270. The probability of being a Republican is 150 over 270. The probability of being a male is 140 over 270. The probability of being a female is 130 over 270. So the expected value under the expected values of the counts here under the null hypothesis is just the joint probabilities assuming independence between these categories. So if there's no relationship between party registration and gender, then the probability of being a Democrat and a male is simply the joint probability, the probability of being a Democrat, which is 120 over 270, times the probability of male being 140 over 270. So that joint probability is 0.230. And if I want to get the expected value, I just multiply that 0.230 times the total sample size of 270. And likewise for all these other values, right? So the probability of being Republican and female is just the probability of being Republican times the probability of being a female. So if I want to get the expected value, assuming no interaction between the public, assuming the null hypothesis is true, that there's no interaction between the rows and the columns, I just take this joint probability and multiply this by n. So let's go back to our 3x2 table and see how this works. So I have this 3x2 table here that I've typed in. I can say x squared equals chi-square test m. And this spits back, the p-value is 2.95, and the degrees of freedom are 2. The degrees of freedom turns out to be the number of rows minus 1 times the number of columns minus 1. It's if I give you the row sums and the column sums, how much information do I need, given the row sums and the column sums, to fill out the rest of the table. So it turns out if I have the row sums and I have the column sums, and you gave me any 4 of these numbers, I could back calculate the other 2, and that's why the degrees of freedom is only equal to 2 here. So the observed data, so this chi-square object that we get back has the observed data, that's just the data that we put in, so that's not particularly tricky, and has these expected data. And again, let's demonstrate that this expected data has to do with just multiplying the row sums and the column sums together under null hypothesis that there's no interaction. So these are the expected data. I can get the row sums and the column sums really easily in R, right? We can use our magic apply function. So the row sums of our table is just apply M1 sum, those are the row sums. The column sums of our table is just apply M2 sums, those are the column sums, right? So the expected value for my 3 rows and my 2 columns, the expected value is just the row sum times the column sum divided by n. So then my expected vowels show up here, and these are the same expected vowels that are over here. And then my chi-square sum is just the sum, right? I take all 6 of these values. This is just the sum of these 6 values, minus the sum of the observed values squared, right? So the expected values minus the observed values squares, divided by the expected value. That gives us a chi-square sum of 30. Again, the degrees of freedom we evaluate at 2 because it again turns out the rule for chi-squares is that it's simply the rows minus the columns. Rows minus 1 times columns minus 1 is the degrees of freedom. So like we've been doing all semester, we can do a sanity check to make sure that when we perform a test in which the null hypothesis is true, the resulting p-value should be uniform. So here I do a chi-square test on a table with 3 rows and 4 columns. A bunch of times, 10,000 times, I basically fill the spreadsheet with random numbers. Here I'm sampling from the column and row indices themselves, but I could just as easily chosen any other way to get random integers in there. But the key is that the rows and the columns have no relationship to each other, right? I'm just populating the rows and columns randomly. I'm not having any kind of constraint where the rows and the columns have a relationship to each other. So when I run the chi-square test on the resulting table, the p-value should be uniform, and that's what happens, right? So this is just another demonstration that when you run a statistical test when the null hypothesis is true, you get a uniform distribution of p-values. And in this case, the null hypothesis being true means that there's no constraint on the rows for how the columns are populated, and no constraint from the columns on how the rows are populated. And that's certainly true when you populate both the rows and the columns randomly. Now, what's interesting about the chi-square test is that we could use it a second time on this data set, because the chi-square test can itself be used as a statistical test to say, are these values uniform? So if you think about it, our expectation of the uniform distribution is that there's an equal number of observations in each bin. Now, they're not exactly an even number of observations in each bin, right? Because we don't have an infinitely large sample size, so the law of large numbers hasn't given us complete protection, right? And so just by chance, there's a few less p-values in this bin and a few more p-values in this bin. And we can use the chi-square itself to test the hypothesis that this distribution is actually indistinguishable from the uniform distribution. So in order to do this, conceptually, what we're going to do is we're going to break this bin down. Let's say there's 100. Let's say there's 100 bins in this histogram, right? So this is the first bin corresponding to a p-value of between 0 and 0.01. This is the second bin between 0 and 0.02. Let's say that this is the number of p-values that we observed in this particular bin. This doesn't match up exactly. This is made up data, so it doesn't match up exactly here. But let's say that the number of observed p-values in the first bin was 11, and the second bin was 9, and then the third bin was 12, and so on and so forth, down to the very last bin, the 100th bin, corresponding to a p-value of 1. And let's say that's 9. That's what we observed. That's what we expect. This is a chi-square test. We can run this. We can say, is observed minus expected squared divided by expected, is that significantly different than you'd expect from chance? Right? So in this code here, this is the same code that we ran before. We're just going to use this code to generate a p-values from the chi-square test. So every one of these, we do this, let's see, 1,000 times. So 1,000 times we use the chi-square test to generate a p-value on our random matrix. Right? This is our random matrix, right? We expect these p-values to be uniformly distributed, right? So we get these 1,000 p-values, right? And then we ask, okay, if we bin these 1,000 p-values in 100 bins, this is what we observe. Is that significantly different from the expected distribution of p-values that we got, right? And here we see that when we run this, the answer is no, right? So we use the chi-square test again to test our null hypotheses uniformly distributed or not, or the p-values from the null hypotheses uniformly distributed. The null hypothesis here is that the observed equals the expected within random variation, and that's exactly what we get. We fail to reject that null hypothesis with a value of 1. So we can say, okay, yes, this distribution of p-values really is uniform. And for the first time this semester, we can put a p-value on that assertion that the p-values of distribution that the distribution of p-values is uniform. We can put a p-value on assertion, and we can do that with a chi-square sum by looking at the difference between the observed and the expected. So we run our own chi-square test to do that as well. And of course, if we just type QQ uniform on those p-values, this is the plot we get, right? But now we can put a p-value on the null hypothesis that this distribution is not uniform. And of course, it is uniform. So this is sort of nice. So it shows you the flexibility of the chi-square test. If you have any expected distribution and observed distribution, you can use the chi-square test to ask whether the expected distribution is different from the observed distribution. So the chi-square test is a very useful test to have in your arsenal. It's an extremely flexible test.